Hello, this is Modumath Tape 2.2. The subject is renaming fractions. We'll be working with the number line, so make sure you remember it. We'll also be factoring whole numbers, so review that topic if necessary. Modumath Text 2.2 goes with the tape. Open to this text now. If you have any trouble with the material or the machine, ask someone to help you. You've all had some practice locating fractions on the number line. Here's the line segment from 0 to 1. The midpoint has been labeled 1/2. Let's divide each of these halves in half again. The segment is now divided into 4 parts, so we use fourths or quarters to label the points. The first is 1/4, the second 2/4, and the third 3/4. But the two fractions, 1/2 and 2/4, label the same point. Since the points themselves stand for numbers, the two fractions must represent the same number. This isn't news to you. We all know that in American money, a $1/2 represents the same amount as 2 quarters. On a clock, a half hour is 2 quarter hours. And when you're aiming at a target, you're doing as well scoring 1 bullseye out of 2 tries as 2 bullseyes out of 4 tries. No matter how you look at it, these two fractions, 1/2 and 2/4, stand for the same number. But let's get back to the number line. What happens if we divide each quarter in half? The line segment is now divided into 8 equal parts. So we label the points in eighths. 1/8, 2/8, and so on. Some of these fractions label new points, but others, 2/8, 4/8, and 6/8, are simply new names for points we've already seen. What we're really doing is renaming fractions. Here, the line segment is divided into thirds. If we divide each of them into thirds again, we end up with 9 equal parts. So we label in ninths, 1/9, 2/9, and so on. Again, some of these fractions label new points, but others, 3/9 and 6/9, to be specific, are merely new names for points we've already worked with. One last example. Here, the segment is divided into halves, thirds, and sixths. Pick out the pairs of fractions that label the same point. Did you see that 2/6 is another name for 1/3? 3/6 is another name for 1/2? And 4/6 is another name for 2/3. If not, replay the last few minutes of this tape. Otherwise, you're doing fine. By now, you probably recognize that two fractions can actually be interchanged in the sense that they label the same point on the number line and therefore stand for the same number. But we can't drag in a number line every time we want to rename a fraction. We need an easier way, and we'll find it by returning to the arrows and targets. We're interested in comparing the number of bullseyes with the number of tries. We know that 1 bullseye out of 2 tries represents the same degree of success as 2 out of 4 tries. This is because we doubled the number of bullseyes from 1 to 2 and the number of tries from 2 to 4. Suppose we have 6 tries. How many bullseyes do we need to keep the same ratio? You're right, 3. 3 out of 6 is like 2 out of 4 or 1 out of 2. In fact, if we multiply both bullseyes and tries by any number at all, the ratio of bullseyes to tries will always be the same. And this gives us the rule we're looking for. One way to rename a fraction is to multiply both numerator and denominator by the same non-zero number. It can be any number at all as long as it's not 0. We call this multiplying through by the number. Let's summarize the rule. If a over b is any fraction and c is not equal to 0, then a over b equals a times c over b times c. In other words, we're allowed to multiply through by c. Here's an example. Start with 3/5. Multiplying numerator and denominator by 2, we get 6/10. Multiplying through by 3, we get 9/15. Multiplying through by 4, we get 12/20, and so on. Again, each new fraction is a new name for the original one, 3/5. Try this one yourself. Start with the fraction 3/4. Rename it by multiplying numerator and denominator by 2 as shown. The answer is 6/8. 3/4 equals 6/8. If you had any trouble, check with someone who can help you. Otherwise, you're ready to go ahead. In renaming fractions so far, we always ended up with larger numerators and denominators. This is called renaming in higher terms. But often we want to rename a fraction in lower terms. This is called reducing the fraction. Suppose, for example, we're asked to reduce the fraction 15/20. Maybe you remember what to do. You examine the numerator and denominator and recognize that each is a multiple of 5. So you divide numerator and denominator by 5. Or, as we say, you divide through by 5. The result is 3/4. We've renamed 15/20 in lower terms. We can write it out as shown, or use this shortcut, which is probably familiar to you. Suppose we're asked to reduce 12/30. We notice that 12 and 30 are both even numbers, so we divide through by 2. This gives us the fraction 6/15, but we're not done. Since 6 equals 2 times 3, and 15 equals 5 times 3, we can also divide through by 3. The final result is 2/5. Returning to the original fraction, 12/30, we could have done the job in one step, dividing through by 6. But the two-step method isn't wrong. What gives us the right to divide through in the first place? Why are we so sure that the new fraction will be a new name for the old one? Because equality is a two-way street. If we can go from left to right, we can also go from right to left. A little while ago, we started with 3/4. Multiplied numerator and denominator by 5, and obtained 15/20. Well, if multiplying makes it possible to express fractions in higher terms, it's reasonable that division will do the reverse. Starting with 15/20ths, we divide numerator and denominator by 5 and return to 3/4. Now we have two ways to rename fractions. We can multiply numerator and denominator by the same whole number, and we can divide numerator and denominator by the same whole number. Multiplying expresses the fraction in higher terms. Dividing reduces it to lower terms. Of course, we can't multiply or divide through by 0, but we still have two important questions on reducing fractions. First, how do we know what to divide through by? And second, how do we know when we're done? We'll answer the two questions together. We'll work with the earlier fraction, 12/30ths. The first step is to rewrite numerator and denominator as products of primes. You learned this in the section on whole numbers. It'll come back to you as you work. For example, since 12 equals 2 times 2 times 3, and 30 equals 2 times 3 times 5, we can write 12/30ths as 2 times 2 times 3 over 2 times 3 times 5. This immediately shows us that we can divide through by 2. In the numerator, be sure you cross out only one of the 2's. Leave the other one alone. Canceling must always be done on a one-to-one basis. What happens in the numerator must be exactly the same as what happens in the denominator. Anyway, we cancel 2's and we're left with 2 times 3 over 3 times 5. Since the 3 appears in both numerator and denominator, we can also cancel the 3's. We're down to 2/5, and there are no more common factors, so we're done. We have reduced the fraction to lowest terms. Let's reduce 20/42 by the same method. The prime factorization of 20 is 2 times 2 times 5. The prime factorization of 42 is 2 times 3 times 7. So we can rewrite 20/42 in terms of these factors as shown. We begin by dividing through by 2, leaving 2 times 5 over 3 times 7. And that's it. There are no more common factors, so we have to stop. The answer is 2 times 5, or 10, over 3 times 7, or 21. Notice that neither 10 nor 21 is a prime number. Each of them has factors of its own, but they don't share any factors. We say they are relatively prime. Relatively prime means prime compared to each other. Once the numerator and denominator of a fraction are relatively prime, the fraction is in lowest terms. Try reducing the fractions shown. They also appear in your Modumath text as Exercise 1. In the first problem, we've started it for you. If you happen to notice some common factors, you can divide through at once. Then apply the method of prime factorization to whatever is left. Here are the answers. We've shown the prime factorization in each case, but maybe you didn't always need it. At this point, it's fair to ask, why do we bother to rename fractions? Who needs it? We'll answer this in the next few lessons. As you'll see, for adding, for subtracting, and for comparing two or more fractions, renaming fractions in higher terms will be essential. On the other hand, reducing fractions is mostly a matter of convenience. For most mathematical purposes, 3 million over 4 million is every bit as good as 3 over 4. Anything you can do with one, you can do with the other. However, it's a lot easier to work with reduced fractions. The fraction shown happens to equal 1/3. But which one makes you feel more at home? You can think of all fractions as organized into infinitely big families or classes. For example, 1/2, 2/4, 3/6, 4/8, 5/10, and so on, all belong to the same class. Every fraction belongs to one class, and within each class, all the fractions stand for the same number. Let's look at some particular examples. We know that the whole number 1 can be written as the fraction 1 over 1. It won't change the value of the fraction to multiply numerator and denominator by 2, giving us 2 over 2. In this way, we get 1 equals 1 over 1 equals 2 over 2 equals 3 over 3 equals 4 over 4 equals 5 over 5, and so on. In short, any time the numerator and denominator of a fraction are the same, that fraction is a member of this class and is equal to 1. The other type of fraction we're interested in is the type with a numerator of 0. We know that 0 over 1 is another name for the whole number 0. Multiplying by 2, 3, 4, 5, and so on, we get the class of fractions shown. Any fraction with a numerator of 0 is a member of this class and is equal to 0. Let's review the important ideas of this tape. First, we saw that you can multiply the numerator and denominator of any fraction by the same non-zero number. The value of the fraction will be the same. Then we saw that we can also divide numerator and denominator by the same number, or, to use a more familiar word, we can cancel. These two procedures allow us to organize fractions into whole families or classes, all equal to each other. We were especially interested in two of these families. There's the one in which numerator and denominator are the same. Every member of this family equals 1. And there's the family in which the numerator is 0. All of these equal 0. If you had any difficulty with the ideas of this lesson, replay the tape or ask someone to help you. Otherwise, you're ready for the problem session in your ModuMath text.